So I'm going to talk about correlated resetting gas, and I'll explain to you what I mean by that as I go along. And this is a sort of recent series of work which was done in collaboration with Marco Biroli, who is my graduate student. He's the next generation of Birolis. And then Manas Kulkarni, Hernan Laralde, Sanjeev Savapandit, and Gregory Sher. And these are sort of published in some recent references. The last one is about quantum gas, which I won't have time to talk about today, but I'll mostly focus on classical resetting gas, and I'll explain to you what I mean by that. All right, so here's the sort of outline of my talk. So I'll first take some time to explain to you a little bit, remind you a little bit about a correlated gas, strongly correlated gas in thermal equilibrium in one dimension, for example, and what are the main observables that one is interested in. And this is a very age-old subject, but it has seen a revival due to recent cold atom experiments and so on. And then I will talk about again, a strongly correlated gas, but now in a non-equilibrium stationary state, and which will be created by stochastic resetting that you heard about yesterday in Shupriya's talk and Sir John's talk. And then I'll talk about some physical observables. Some of them are macroscopic, like average density of the gas, and then, the extreme statistics or the spacing distribution between particles, and then full counting statistics. I'll explain to you as I go along. And finally, I'll summarize and conclude. Okay, so that's the plan. So let's start with just a very simple system of one-dimensional correlated gas in thermal equilibrium. What do I mean by that? So imagine that you have, you can define it in any dimension, but for simplicity, I'll just focus in one dimension. So you have a bunch of particles on a line, and they are subjected to a confining potential V of x, which could be harmonic or anything. And so configuration is specified by the positions of the particles. And so these particles are in general interacting. So the energy of the gas for a given configuration, you can specify the energy. So there's the external potential term, which is this V of xi. And then, of course, you have interaction. You can have a two-body interaction. You can have three-body interaction. Very generally, you can have any sorts of interactions. They could be short-range or long-ranged, whatever. So this is the very general setting of a correlated gas. And so in thermal equilibrium, as all of us know, that the joint distribution of the position of the particles, which means that the probability of a given configuration is given by the Gibbs-Boltzmann weight, which is e to the power minus beta, which is the inverse temperature times the energy of the configuration. And there's a normalizing constant, which is the partition function. So this is the textbook stuff. Okay. Now, of course, here we know the equilibrium measure exactly, but even knowing that, to calculate several experimentally measurable observables are not that easy. And as I said, this is an age-old problem, you can find in any textbooks, but typically, in textbooks, you have a sort of interacting gas, but they are considered, usually it's considered as a homogeneous system, and like in a big box or something. But in the cold atom context, where this is an optical trap generated, in the lab, and where the particles are confined, so there the system becomes inhomogeneous. So it's not translational invariant anymore. And as a result, many things can change, as we'll see, in a short while. And so one would like to understand, for example, that, given this probability measure, what can we say about the different observables? And the main point here is that in presence of interactions, okay, so this joint distribution does not factorize into individual marginal distributions. It will happen if the red terms are all zero, that means a non-interacting ideal gas. So in that case, there will be perfect factorization. But if they are correlated, you cannot, and this is the main source of technical problems of calculating any observables. So what kind of observables you are talking about? So there are many observables. It could be, as I said, this is an inhomogeneous system. So the first thing you can ask is, what is the average density? So in an ideal gas in a box, of course, the density is uniform, constant. But here, because of the trap, confining trap, the density itself, which is just the fraction of particles between, average fraction of particles between x and x plus dx. And so that object itself has a non-trivial x dependence, it's inhomogeneous. So that's a macroscopic observable, which you can easily measure in the experiments. And then you can go for microscopic observables. For example, I can, order the positions x1, x2, x3, xn in increasing order. So m1 is the position of the rightmost particle, m2 is the second rightmost particle, and so on. And so these are called order, and you can ask the statistics of them. So for example, you can ask, what is the distribution of the rightmost particle position, so which is the maximum of these guys, what is the position of the next rightmost particle, and so on. So that's called the order statistics. And you can ask for the spacing, that, what's the typical spacing between the particles in equilibrium. And you can ask the distribution of the spacing, not just the average spacing, but you can ask the distribution of the distance between the kth particle position and the k plus 1th particle position. So this is called the kth gap, essentially. Then you can ask other observables like full counting statistics, which means that I take an interval minus L to plus L, and I just count the number of particles inside this interval, and that's a random variable fluctuating from one configuration to another configuration. You can ask what is this distribution of this number of particles inside this interval. Okay? So these are the standard observables that people try to compute or measure in experiments and so on. So these are the sort of main observables of interest. Okay? So here the problem is very well defined. You have given me the equilibrium measure. So after that, it's a technical problem. Given this equilibrium measure, how do I calculate these objects? And that is the usual statistical mechanics, essentially. Okay? Now, of course, it's very generally hard to compute for a correlated interacting gas because you cannot factorize this distribution here. Okay? So interactions make it very difficult to compute these objects. So there's one case which is this when there is no interaction, which is the ideal gas in an external confining potential. So in that case, as I said, the joint distribution, which is just e to the power minus beta exi, and it just factorizes because there is no interacting term. And each of these p of x is just e to the power Gibbs weight, e to the power minus v beta x divided by the normalization constant. So in that case, it's very easy to compute all these observables that I mentioned. Okay, so just to show you how to compute this, is a trivial exercise. In fact, so for instance, if I want to calculate the average density, that's even simple because average density means that this object here, and it's very easy. If you just take this measure and calculate, obviously it's going to be p of x itself. So if you know p of x, then you know that what is the average density of the particles. These objects are a little bit harder to compute, but not that difficult. Okay, still, once you know this marginal distribution p of x, which is e to the power minus beta v of x, you can calculate all these observables very easily. For instance, if I want to look at the order statistics, that is the probability distribution of the kth maximum. So what you do is you just take one of the guys to be at, let's say I'm asking what's the probability that the kth maximum has a value w. So that means one of them has to be w, then k minus one of them has to be less than w, and n minus k of them has to be bigger than w, and they are independent, so it's a product. And there's a combinatorial factor because this guy can be any one of the n guys essentially. Okay, so it's very easy. So it's explicit in terms of this p of x. You give me p of x, I can tell you what is the order statistics, and you can analyze this. Similarly, the gap statistics. For that, I need the joint distribution of mk and mk plus 1, the position of the kth particle and k plus 1th particle. Once I know the joint distribution, which can be again written down explicitly in terms of p of x, you can actually compute the gap distribution and so on. And similarly, the full counting statistics, which is the probability distribution of the number of particles between minus L to plus L. So this is the random variable. So clearly, these particles are independent, so therefore it just has a binomial distribution where QL is the occupation probability. That means what's the probability that one of the particles lie between minus L to plus L. Okay, so this is just a QL. So once you know QL, which you know of course because you know P of x, so you can actually compute the full counting statistics also. So basically what I'm saying is that in absence of interaction, all these observables can be explicitly computed in terms of this P of x, which you know also explicitly. Okay, but of course, when you have interaction, it becomes much more difficult problem. So there are two types of interaction. So it could have a short range interaction, which means there is a finite correlation length in the system, and so then there are still methods by which you can compute these observables, for example, using perturbation theory or normalization group method, etc. But the problem becomes more complicated when the system is long ranged, which means that the correlation length is bigger or comparable to a system size. So all the particles are very strongly interacting. So there, it's much harder to compute these observables. Okay. And there is no general method for that. Okay, so in a recent book that we wrote with Gregory Sher, so there's some of these examples are discussed there. So just to show you that one example of a strongly correlated gas, this is the famous Dyson's log gas in one dimension. So which means that here the particles are again confined in a harmonic potential, and you scale with the factor n in order that all the positions are of order 1. And then there's the interaction, which is the two-body interaction, pairwise interaction between all the particles, okay? And this interaction is repulsive, and it behaves like log of xi minus xj in one dimension, okay? So it's not really Coulomb interaction. Coulomb interaction is log is only in 2 dimension, but here, although they are repelling each other by 2-dimensional Coulomb interaction, the charges are confined on a 1D line. So this gas is particularly very well known because it appears very naturally in random matrix theory. So just to very briefly tell you where this gas appears. So imagine that you have a n by n matrix whose elements are independent apart from the symmetry, that is a Gaussian Hermitian matrix, and each element is independently Gaussian. Hij is the element of the ijth element of the matrix, and they are independent Gaussian. So therefore you can write down the joint distribution of the entries of the matrix as a product of the individual Gaussian distributions. And if you choose the variances in appropriate way, you can write this as exponential minus n trace of h dagger h. And so the point about writing this, it means that if I make a unitary transformation of my change of basis, okay, of the if you think of this as a random Hamiltonian, then this probability distribution of the entries is independent of the basis, okay? And this is the famous Gaussian unitary ensemble of random matrix theory. Gaussian, it's called Gaussian unitary ensemble because it's invariant under unitary rotation. So this is the joint distribution of the entries. And the whole game of random matrix theory is to ask what is the joint distribution of eigenvalues. So you give me the matrix, I can diagonalize it because it's a Hermitian random matrix, so you have, all the eigenvalues are real, and you can ask what is the joint distribution of the eigenvalues. And it turns out that these joint distribution of eigenvalues, they are strongly correlated. In fact, this joint distribution was computed by Wigner long back. So it has this of this form, which is exponential minus n lambda I square, and then there's the repulsive term, which is lambda I minus lambda j square. Okay, so this is I less than j for every pair. So this is called the van der Monde term, basically. And without this term, again, it will factorize, so it will be ideal gas, basically. But because of these repulsive terms, and this is the famous eigenvalue repulsion that people use in nuclear physics, for instance, that the eigenvalues, they don't like to be next to each other because this probability vanishes when the two eigenvalues are very close to each other, okay? And in fact, you can write down this lambda square as e to the power 2 log of lambda, and therefore you can cast it in the language of the one-dimensional correlated gas. And what you see here is that the energy of the gas is just a external harmonic, potential, and then logarithmic repulsion. And so lambda i's you can interpret as the positions. So eigenvalues you can interpret as the positions of a gas on a 1D line, and with a pairwise log repulsion. And that's why this is the example of. So if you know all these observables like spacing distribution, or the right average density and so on. So those are actually computed for the log gas or random matrix theory for a very long time. The whole, there are many books on this subject, and you can compute exactly, but they're not that easy to compute. Okay. So for instance, if you look at the average density, so you would expect more particles to be near the trap center. So the trap is like this. So trap center there will be more particles, and as you go away from the trap center, the particle density will decrease. And in fact, this is the large n limit, the scaled variable, the density, is given by the famous Wigner semicircular law, so which is this semicircular law. So there is more density at the center, and then it goes to 0 at the edge. And then, people have calculated, for example, the distribution of the M1, which is the largest eigenvalue. So this is given by the famous Tracy-Widom distribution, which says that on an average, the largest eigenvalue is located at the edge of this density, Wigner's semicircular law. But there are fluctuations, and fluctuations of order n to the power minus 2/3, and then you can actually compute the distribution around this width fluctuation, and this is the Tracy-Widom distribution. You can also calculate the several large deviation probabilities and so on. I'll not go into the details. There's a huge literature on this subject. There are books and review articles and so on. So, but just to show you that the moment you put strong interactions between the particles, and here it's a strong because everybody is interacting with everybody else, so there is no finite correlation length in the system. Then the problem to compute anything becomes very hard. The whole subject of random matrix theory is essentially to compute these observables, knowing the joint distribution of the eigenvalues. All right. So this is about equilibrium gas where you know the density. Okay, so now I'm switching over to non-equilibrium gas, and what do I mean by that? Strongly correlated gas. So in a non-equilibrium situation, and I'll give you examples of that. So unlike in equilibrium systems, so essentially, the dynamics decides the stationary state, and the dynamics typically violates the time reversal symmetry or the detail balance, if you like. So often we don't even know what is the joint distribution of the particles in a non-equilibrium stationary state. It's not given by Gibbs measure, and it's typically very hard to compute, okay, explicitly. So that's the number one problem, that we don't even know which measure to start with. Okay. In equilibrium system, at least that part is there, that is, you know which distribution to start with. But here we don't even know that. That's number one problem. And number two problem is that even if we can determine somehow this joint distribution explicitly in the stationary state, computing these observables like average density, extreme order statistics, etc., they are typically very hard due to the presence of the strong correlations. Okay, so the goal, at least for this talk, would be that to find some systems which are, interacting many-body systems which are in a non-equilibrium stationary state. Number one, they are strongly correlated because that's the interesting part about it, and they're still exactly solvable for these observables. Okay, so can we construct a class of models, for example, simple models, where these three properties hold? Okay, and what I want to show you today is that indeed it's possible to generate a whole family of models which actually satisfy all the three properties, and this is actually done by stochastic resetting. And so what I'll do is, even though this was discussed yesterday by Supriya and John, I'll just remind you, for those of you who are not familiar with stochastic resetting, just very briefly about what is stochastic resetting, and then how we can use stochastic resetting to generate a strongly correlated gas in a non-equilibrium stationary state. Okay. So stochastic resetting is a sort of subject which is relatively young in statistical physics, about 30 years old, but it has seen quite a bit of developments, both theoretical and experimental, over the last decade or so. And there have been many problems, and there's an explosion of activities because there are many applications of this basic idea, and there are various review articles. Arnaud was involved in one of the reviews, and and so many other people in this audience have also worked on it, as you heard yesterday. And so let me just very briefly tell you what is stochastic resetting. If you don't know anything else, it's very simple. So imagine that you have any system which could be deterministic, stochastic, classical, quantum, any system, whatever system you have, and x of t is just the degrees of freedom. It could be just the position of a particle, or it could be just a configuration, and this is time. So it has its own natural dynamics, which again could be deterministic, stochastic, classical, quantum, whatever. So you evolve it up to a random time, tau 1, and after this random time, you just reset back to its initial configuration, initial or any other configuration if you like. So you don't let it evolve indefinitely, you just stop it at random time and you go back to the initial state, and then you restart the dynamics again. Again, it goes by natural dynamics, and after some random time tau 2, drawn from the same distribution p of tau, again you reset and you will let it evolve. That's it. So it obviously has a renewal structure inbuilt into it, because once you reset, it forgets about the memory of the previous what happened before previous reset. So all you need to take care of is what happened after the last resetting. Okay, and these intervals tau 1, tau 2, tau 3, they are statistically independent, and this is the sort of renewal process structure. And the most popular resetting protocol is you choose this from an exponential distribution, r e to the power minus r tau. This is called Poissonian resetting, where 1 over r is the typical time scale between two successive resettings. Okay? So r is like a rate of resetting. So if you do that, then what happens is that in long time limit, in many situations, the system reaches a stationary state, and we'll see that in a minute that this stationary state is actually a non-equilibrium stationary state. To see this, let me go back to the original example that just a simplest example is just a single particle diffusing and then resetting. So this is the example which was discussed by Supriya yesterday. And So just think of it just in one dimension as a simple model. You have a single particle which is diffusing, and then after some random time with rate r, you reset, and then it goes on like this. Okay, so essentially, if you are doing Monte Carlo simulation, you would write down your update dynamics, if you like, position of the particle at time t plus delta t in continuous time. T plus delta t will either be 0, and this happens with probability r delta t. So r is the resetting rate, and with the complementary probability 1 minus r dt, you just evolve it by just adding a random noise, white noise, with the d is the diffusion constant, and this is just a Brownian diffusion. Okay, so this is it. So r is the only parameter in this model, and this is the sort of model we introduced with Martin Evans 12 years back. No, now it's 13 years back, 14 years back. And this is the sort of the starting model, and it's very simple to analyze this model. And you ask, first thing you can ask, what happens in the long time limit? Now there are many aspects of stochastic resetting. There's a mean first passage time to find the target that Supriya had discussed and John also discussed yesterday. But one of the principal things is that this is a very simple way to generate a non-equilibrium stationary state. Okay, and let's see how you generate such things. So how do you solve this problem? So it's very easy. So essentially, okay, you want to calculate what is pxt, probability distribution the particle arrives at x at time t, and given the resetting rate r. You start from the initial condition delta of x. So if there is no resetting, you all know that the distribution is just a simple Gaussian, e to the power minus x square over 4 dt. And so now the question is, if I switch on the resetting rate r, what happens to this distribution pr of xt? Okay. So how do you calculate this? It's very simple. So you can write down a Fokker-Planck equation for this. So del p del t is there's a diffusive term which is on the right hand side. So this is what you would get in normal diffusion. But now, because of resetting, if you are at x with rate r, you are going away from x. So this is a loss term, and there's a gain term, which is that if you happen to be at x, you can come from any other point by resetting there, and this is just a source term essentially at x. And so this is a partial differential equation, and you just have to solve this problem with the initial condition is this, and this is quite trivial. I mean, you can do by Fourier transform and whatever, but the solution you can write it in a very simple way, which is quite suggestive, and this is the exact solution at all time t. So in this solution there are two terms. So the first term is actually, the meaning of it is that if you look at the trajectory, there is a possibility that you don't have any resetting between 0 to t. The probability for that is e to the power minus rt, and then it's a free propagation. So this is just p0 of xt, which is just a Gaussian propagator. Or you can have one or more resettings. In that case, you just keep track of the last resetting. Okay, so this is the last reset, because you don't care about what happened before that. At this time you have just certainly been reset. So basically the history starts from here. Okay, except so here from 0 to tau you have a free propagation, but the tau, the time since the last resetting, is itself is a random variable, and its distribution is just simply exponential. Okay, because you have no resetting up to time tau followed by one resetting event, which is r d tau, and then you have to integrate this tau from 0 to t. Okay, you can check that this is the exact solution of the differential equation, but this is a very nice renewal interpretation of this resetting object. And what you see is that in the long time limit, if t goes to infinity, this term drops out, and essentially, and this integral you can do it trivially, and this is just a exponential minus alpha naught mod x, where alpha naught is square root of. So this is the length scale. This is the amount of distance that the particle travels between two successive resettings. That's the natural length scale here, inverse length scale. And so this is the sort of simplest prediction. And you see that this is a non-equilibrium stationary state. So it is a non-Gaussian. It has a cusp at the origin, at the resetting point, and it decays exponentially on both sides. So even though it looks like as if it's a Gibbs distribution with an effective potential which is mod x, it's actually a non-equilibrium distribution, because by resetting, you actually violate Dittel balance, because you are coming from some long, far away point to the origin by resetting, where there is no reverse move. So it manifestly violates Dittel balance. So there is a probability current flowing around in the configuration space, and therefore this is a non-equilibrium stationary state. It's a very, very simple example of this. And so this was a prediction, and quite recently from the group of Yael Roitman, so they could measure this experimentally using a holographic optical tweezers, and you see that it matches between experiments and theory very well. Okay, so this is how. So today I'll just focus on the non-equilibrium aspect of it. So let me now go to the. So there is another experiment which was done from the group of Siliberto in ENS Lyon, and this was actually again using optical trap setup, and this was discussed by Supriya yesterday. So essentially what you do is you let the particle diffuse for a random time, and then you switch on, this switching on an external potential. So if you take a harmonic potential, you switch on, so that confines the particle, so that mimics the resetting essentially. And during that time, you don't make any measurement. So, and if you make this potential steep enough, it's almost like resetting to the initial position at the center. And then you switch it off, the potential, and let the particle again diffuse freely for a random time, and then you switch on and switch off. So these two steps alternate. So this is how, the originally, it was also measured in this experiments in Siliberto. And so this question naturally motivated us then to ask, what happens if I, instead of one particle, if I have multiple particles here, okay? And so now you have, let's say, for a simple case, you just think of n non-interacting particles, okay? And you let them freely diffuse up to a exponentially distributed random time. Then you switch on the potential, let the particles equilibrate, and then you switch on and switch off and so on. Okay, just to alternate. So as I said, this is just mimics the instantaneous resetting to the origin. Okay, and of course, in real system, of course, you might have interactions, but as in these days, you can actually tune interaction by using all kinds of tricks in cold atom systems. So we decided to look at just this simple non-interacting particle. So the model is very, very simple. So in one-dimensional line, you have n particles. They are independent, n independent Brownian motions. They evolve, and then they are simultaneously reset to the origin by the trap, and after some random time with rate r. And you can ask, what is the joint distribution of the particles after some time t? And again, this is a non-equilibrium situation here because of violation of Dittel balance. So again, using this, very general renewal equation that I mentioned to you. So again, there will be no, exact solution of this at any time t. There is a term which is no resetting, so which is e to the power minus RT when there is no resetting up to time t. And then you have a free propagation, and because the particles are independent, so it's just a product of these individual Gaussian propagators. And then when there is one or more resettings, you look at the time since the last resetting event, and this is a free propagation again. And then you have to multiply by the distribution of tau, which is exponential, and then you have to integrate from 0 to t. Okay, so very, very simple. Okay, the particles are sort of, to start with, they are non-interacting, but what you see, okay, in the long time limit, again this term will drop out, and you reach a non-equilibrium stationary state, which is given by this object. Now the interesting point here is that you see that this distribution obviously does not factorize. It factorizes inside the integral. But when you integrate over tau, they no longer factorize, which means there are non-trivial correlations between the particles, which is dynamically generated by this simultaneous resetting. See, the particles are going around, but when you simultaneously reset them from time to time, they somehow, remember this, and this generates dynamically a correlation which persists all the way up to the stationary state, and you get a non-trivial non-equilibrium resetting gas where the joint distribution does not factorize. Okay. And so you can actually, calculate the correlations. If you calculate just the normal 2-point correlation, it will be 0 by symmetry because of the Brownian propagation, x going to minus x symmetry, this is 0. So you have to go to the next order of correlation function, and next order of correlation function you can calculate exactly, and this is 4d square over r square. So this means it generates an attractive all-to-all interaction, and this is again dynamically because it's like all of us are free particles. You are allowed to roam around, but then there's a bell rings, and then you have to come back to one room, and that generates dynamically the interaction between the particles. Okay? Yeah, will you have a question?
Quick question.
Yeah.
You did do resetting at a given time.
Yeah.
But you reset when they reach the same position.
Yeah. Yeah. You can also, in fact, with Arnav, we are doing some work on this recently. So you can generate all kinds of things. So all right. So this is it. And so the stationary joint distribution therefore has this very interesting form which we call the conditionally independent and identically distributed, which means that they are basically independent except for one parameter which itself is random, And they share this parameter. In this example, this tau, the time since the last resetting, is the parameter, which has an exponential distribution. But in general, it could be from any other distribution. So when you have a structure like that, the nice thing is that you see that inside the integral, inside the integral, inside the integral, this is the ideal gas structure. So you can calculate, as I showed you in the beginning, all the observables for this, and you just have to integrate over this guy. Okay, so that's it. So then you generate all kinds of non-trivial correlated structures, and I mean, you can calculate all these observables exactly. Since there's not much time, I'll just flash the results basically. Okay, so explicit results. So the distribution of the gas is essentially, you can compute very easily. It has again this double exponential distribution. This is average density of the gas. You can calculate the order statistics. So the particles, their typical spacing between them is order 1 over n in the bulk, and near the edge is 1 over square root of log n. And okay, I'll not go into the details, but you can calculate the distribution function, and it's given by a non-trivial function, which is 2z e to the power minus z square, which is universal in the sense it does not matter whether you are probing the bulk or at the edge, unlike in the randometrics theory, and you can check with the simulations, it works perfectly fine. You can calculate the gap statistics. Again, it's a universal function. Universal in the sense it does not matter where you are probing. It's an inhomogeneous system. It's independent of where you are probing the gap, and it's actually given by a non-trivial function, which decays with a sub-exponential decay e to the power minus z to the power 2/3, and you can calculate the full counting statistics, which is also given by a non-trivial scaling function. This is the number of particles inside an interval minus L to plus L. It's given by a non-trivial scaling function, which has a very interesting shape here. It sort of diverges at the edge when kappa is order 1, and you can calculate all the asymptotics and so on. So these are explicit results. Okay, so and then so what you have is that you have a whole class of solvable correlated gas by this CIID structure. Okay. And this is a sort of new application of stochastic resetting, and you can actually take ballistic motion, not just diffusive, Levy flights, and so on. And you can also use 2 different experimental protocols. So the first protocol is that you take a harmonic potential, and you just change the stiffness with rate R1 and R2. Just go back and forth between 2 stiffnesses, and again this drives the system into correlatedness. And you can actually calculate, and it has exactly the same CIID structure. And the second protocol is with Sanjeev. So we looked at the harmonic well, where you actually take the center and you just make a stochastic motion of the center. And that itself, because they all have the common center, that introduces correlations between these particles, which you can compute explicitly. And all of them have this structure of CIID structure, which allows us to calculate everything explicitly. Okay? So let me summarize. So essentially, what we have is, we have a full family of solvable correlated gas with a non-equilibrium stationary state, and it has a sort of the mathematical structure which allows us to calculate everything explicitly. And there are various examples. I mean, this is the protocol I mentioned here. So Silibatu is now doing the experiments to measure our predictions, and so this, so it's very rare to find strongly correlated system, and that too out of equilibrium, for which you can calculate various observables which are measurable experimentally, and this is what is done by this system. So let me just end with a sort of advertisement of our recent book with Gregory on statistics of extremes and records in random sequences. So some of the ideas that I discussed today, this is a very recent book which came out in the last July, and about the correlations and order statistics and so on, strongly correlated versus weakly correlated system. So these are discussed here if you are interested. Okay, thank you very much for your attention.
The correlations are mediated by that resetting time, right? The taus are, for example, are xi and xj correlation.
Yes.
Happens through what? Is there a potential?
No, there's no. That's the whole point I was trying to say. It's created dynamically.
Right.
So imagine that again. In this room, we are all free particles. Okay,
right.
We are freely roaming around, but each of us are carrying a bell. Okay, and when the bell actually only one bell. So when it rings, all of us have to come back to this room. So if you keep doing this, even though between 2 resettings you are totally independent, but the fact that you are actually coming back simultaneously at the same time. So that's the origin of correlations, okay?
Right.
And
So
so
it's mediated by the resetting.
by the resetting,
Right.
essentially,
And
exactly.
like they don't all come back to the same point, right?
Yes.
They all come back to their original points.
Yeah.
Xi comes back to xi0, xj
Right.
comes
No,
back
this
to
was for simplicity that we took the thing that they were all coming back to the origin.
Thank you.
Otherwise, you can do it for arbitrary initial positions also.
Thank you.
Yeah.
So the question was related to this Poissonian resetting. So if you are choosing some different scheme,
Yeah.
then your this
Yeah,
correlation.
the stationary state will be different, of course. I mean, but you can still, the CIOD structure will still hold. I mean, actually, in many problems, what happens is that, I mean, it's hidden. I mean, in the sense that, the joint distribution is not always easy. In this particular example I discussed, it was evident, manifestly built in that e to the power minus r tau, the Poissonian resetting. But for example, in these other problems that I discussed, when you have a protocol where you have the two potential, you are just switching back and forth between mu1 and mu2, it's not obvious at all. You can solve the Fokker-Planck equation, but it's not obvious at all that it has a CIID structure. So you have to identify which is the parameter which has a common distribution, h of u. So that's not always easy. I mean, what I mean by this is so the point is that you can actually calculate this explicitly, but you have to have some integral representation like this. Only then you can actually calculate things. Otherwise, if you have a strongly correlated gas, to calculate anything is very difficult. The fact that it has an integral representation like this is not at all obvious. Okay. In fact, general mathematical question is, if I give you a joint distribution, under what conditions can you write it as a CIAD structure? Okay, that's not known in general. Okay.
Yeah.
So,
Yeah, thanks.
yeah. Abul.
So the reason I asked you this question, I was thinking of a different problem, and these guys know it much. Your geographic vicinity knows this much better than me. There are these elastoplastic models,
Yes.
which is basically a stress diffusion.
Yes.
But as soon as the stress reaches an yield
Absolutely.
stress, it's a resetting.
Exactly. So this is the, this is the,
And these equations have been written down, but there are no formal solutions.
No. I mean, at least in this context, you can actually. So there was a paper by Sid Redner and Benjamin De Bruyn who actually first computed this. So their motivation was that if you look at the electrical network in Canada, for example, okay. So typically there's a blackout when it exceeds, the voltage exceeds certain threshold value. There's a blackout and everything gets reset. I mean, basically to zero. And then so this is what is called the first passage resetting. That means you have a level, and when you hit this level, you reset. So you don't reset randomly at random times, but you reset only when you hit some level.
Right. So I think the people who do this amorphous plasticity thing would benefit from using.
No. In fact, people are already, people like Eric Bachta, they are already using this, for example, okay, for the elastoplastic models, avalanche models, and so on.
Okay.
So this is already done. So And one of the applications of resetting, basically,
Satya, this h of u in the previous case was the time distribution between resets.
right.
What is h of u here?
Here, so here is actually it's a little bit complicated. It's actually the residence time in one of the potentials. So I mean, like you have mu1 x square by 2 and mu2 x square by 2. So if you look at a trajectory, so it spends some time in this, some time in the other potential, some time in the other. Okay. So if you ask, what is the occupation time? If I look at a time t, what fraction of time it spends in potential 1? For example. So U is the fraction of time it spends in one of the potential. Okay. It's not easy to see that directly from this formula that it will be like this, but you can derive this essentially. Okay.
I see. Okay.
So that's what I'm saying. It's not always easy to identify what is the U variable. So sometimes you might be you have an explicit joint distribution. You don't know how to compute things. Okay, but could be that there is a hidden integral representation where you have this structure. That means inside the integral it's an ideal gas, and then you just have one or two parameters which are random. So then it's very easy because you just calculate for the ideal gas. So you have an explicit formula for these things, and then you just integrate over these parameters. Okay. So that's the mechanism of this CIID structure.
And these potentials switch instantaneously.
This potential?
I mean, they switch instantaneously. There is a
there's a R1, R2, but you can actually ask.
No, I mean they don't take once you decide to switch,
Yeah, you switch it instantaneously. Yes. You can ask this question that whether if you do it slowly or something with a time dependent, then what happens? I mean, all this. That's what I was telling you yesterday. The stationary states are actually very sensitive to these kind of things. I mean, it's not.